Hello everyone, welcome to today's presentation. I'm going to talk about our paper Frank-Wolfe merging, scaling model merging with Frank-Wolfe optimization. Model merging is a powerful technique that merges multiple LLMs into one without much performance degradation. However, there are some challenges for existing model merging methods for large-scale setting. First, performance will degrade if irrelevant model is added. And second, performance increase is rather limited when relevant model is added. This is because there is task vector interference. To solve this problem, we propose a method that uses Frank-Wolfe optimization, and here I'm going to talk about a little bit about the background of what Frank-Wolfe optimization is. The Frank-Wolfe algorithm, also known as the conditional gradient method, is an iterative optimization algorithm for constraint optimization problem. At each iteration, Frank-Wolfe first identifies the vertex in the constraint set that yields the largest descent direction, and we move towards that vertex by updating our x accordingly. So it has this form, and it constructs a linear subproblem of the original optimization problem to find that vertex. And after finding that vertex in the feasible sets, we take a careful step from the current position towards that direction, maintaining feasibility through the vertex combination. So how is that relevant to model merging? We first phrase model merging as a constraint optimization problem, just like Frank-Wolfe. In this case, our constraint sets are constructed by our model weights, and we have a loss function which is user-defined. It could be any loss function for any task. Then, there's a possible scaling issue of this formulation. This is because we need to store all the model weights inside the memory when we do the merging. To solve that, we can actually do a reformulation of the loss function as follows. We prove the equivalence in our paper. And a nice property of this reformulation is that the LMO can be simplified to the following form. So, this page shows how we adapt Frank-Wolfe optimization to model merging setting. For the loss function, it is user-defined and operates on a combination of the model weights, and we pick a model weights that satisfy the LMO equation. And for the merge function, it could be user-defined and could be any merging function, but one very intuitive candidate is just simply task arithmetic, which maintains feasibility naturally, and we iterate until the following condition is met. And here is an overview of the algorithm. We evaluate our methods on NLP tasks and CV tasks. So for the NLP tasks, we evaluate on both some discriminative tasks and some generative tasks. And for the discriminative tasks, we use 8 fine-tuned Robota models. And for the generative tasks, we collect 16 open source models from Hugging Face. And we can see for both kinds of tasks, our method achieves better accuracy than existing model merging methods. We also evaluate the following 4 CV tasks, and for the models to be merged, we collect 20 models fine-tuned on 20 different CV tasks. So there are some irrelevant models in the model merging pool. We want to test that whether our model can successfully do the merging, even though there are some irrelevant models. So as can be seen in the table, our method performs the best among all the methods. We also test the scaling performance of our methods, and as can be seen, when irrelevant models are added, our method's performance is relatively constant. This means that it's able to rule out all the irrelevant models from the model merging pool. And for when relevant models are added, the performance steadily increase, which shows that our model has a very good scaling behavior. Here is a cost and performance analysis on merging and also fine-tuning. So as can be seen, our methods achieves good performance with moderate cost. And also it has good data efficiency as compared to fine-tuning and also other data-informed merging methods. Here is an application study. We show the linear approximation of the objective function, and as can be seen, for each dataset, we can successfully pick out the most relevant models using this linear approximation. In conclusion, we extend model merging to a more challenging setting where the merging pool consists of a large number of black box fine-tuned checkpoints, and Frank-Wolfe merging scales effectively with a large number of black box models. Thank you for your attention.